So this might be one of the shortest videos we're going to have because really when we talk about free energy and reaction spontaneity, we're going to be learning a new letter in our thermodynamic alphabet, and really a lot of what we're going to do with this is just a variation on a theme. We are going to have one new equation that we're going to learn about, and then a way to integrate our concepts of entropy and enthalpy. So when we think about measuring spontaneity, we measure spontaneity by using delta G. Delta G is the free energy change. And this again is going to be something that we think about. Spontaneous processes go downhill. But this is a very important equation, really important slide here. This equation will be provided for you, but you want to know how and when to use this. But this allows us to measure the spontaneity for a process by considering contributions from both enthalpy, entropy, and then temperature. So an important concept is to remember that a spontaneous process has a negative delta G. If delta G is negative, a reaction is spontaneous. So if delta G is positive, we'd say that reaction is non-spontaneous. And delta G actually at 0 tells us that a reaction is at equilibrium. So one of the things that we'll expand on in this skill here is understanding that the sign of delta G tells us whether a reaction is spontaneous or not. If it's negative, it's spontaneous. If it's positive, it's not. And the magnitude of it tells us how spontaneous it is and how much product we make. We're going to get to that in our next skill. So a really important equation, a really important slide that just kind of ties all of these pieces together for us. So variation on a theme, and hopefully I don't need to say too much about this skill, we can use the third column in Appendix B to calculate delta G for a reaction. Basically looking up the free energy values for our products, subtracting them from the free energy values for our reactants, of course making sure to scale them up by the corresponding number of moles that we have for each of them. But this is a way that we can calculate the delta G for a process. Another way that we can calculate the delta G for a process is if we know the delta H, delta S values, and the temperature that we are at. But note here, we can use this monster equation to give us the delta H. We can use this monster equation to give us the delta S, and then plugging in the temperature that we're given, that's another way that we can calculate delta G. So lots of ways that we can get at the spontaneity of a reaction. So highlighting here, when we think about this equation, this is going to be a really important equation. If we want delta G to be negative, meaning that's a spontaneous reaction, that confirms that exothermic reactions with a negative delta H are going to help with that. That also confirms that positive delta S values are going to contribute to this. Because if we have something that's negative or already, favorable process, and we subtract more from it, knowing that temperature in Kelvin is always going to be a positive number, we're always going to be adding to the negativity of this process with a positive delta S value. All right, so why are we looking at it like this? Well, sometimes we might have to qualitatively think about and predict the spontaneity for a process. So we're going to talk about 3 different scenarios here. We're going to talk about a win-win scenario, a lose-lose scenario, and then win-lose scenarios that have a temperature dependence. So it all has to do with thinking about this equation, but I'm going to run through some scenarios to help us think about this. All right, so let's think about our win-win situation. So our win-win situation here, so we're going to call this a win-win, is going to be a reaction that's always spontaneous, no matter what the temperature is. So in that case, we must have delta H being favorable, so it's going to be exothermic. Delta H in an exothermic reaction is negative. The reaction entropy must be positive. That's what we know a favorable process is. Negative delta H, positive delta S. And so in that case, it's always going to be a positive number. Try running the math through this. If this is always negative and this is always positive, this is always going to be negative. It doesn't matter what temperature we're at. Okay? And so we have an example here of an exothermic process that has a favorable entropy. That's always going to be spontaneous. And even if we were to look at this and predict the entropy, because we're forming more molecules and specifically more gas molecules as product, that tells us that entropy is favorable. A lot of these things we'll be able to predict. All right, so let's look at our lose-lose situation here. A lose-lose situation means, well, our reaction must be endothermic, that's unfavorable enthalpy. Delta H then is going to be positive. The reaction entropy must be negative, that's unfavorable entropy. And if we look at the math for this, if this is a positive number and we're subtracting something that's negative, that really means we're adding. This is always going to be positive, and delta G that's always positive is never going to be spontaneous. Lots of always and nevers there. But remember, if there's no way that we can make delta G be negative, then that reaction can never be spontaneous. So here's an example of a reaction that does that. It's an endothermic process, and our entropy is unfavorable, but we'd be able to predict that unfavorable entropy. Look at this. We've got 3 molecules of gas going to 2 molecules of gas. Remember that phrase, more molecules moving more? This is less molecules, so that's going to be unfavorable from an entropy standpoint. All right, so what about if we've got win-lose combinations, right? What if we've got reactions where in this case we've got an unfavorable enthalpy, so this is going to be a lose situation, but we've got favorable entropy. This is going to be a win situation. Well, what's the deal there? Well, these are going to be reactions that are temperature dependent, and it has to do with whether entropy is helping or hurting us, because remember, entropy is the part that has a temperature dependence. So in this case, the entropy is a winning piece to our equation. So we want to make that as big and as powerful as possible. So we're going to have temperature in that case be increased to favor this process. So for endothermic reactions that have a favorable entropy, positive delta S, we'd like to have that entropy be more helpful, so these reactions will be favored by increasing the temperature. All right, let's look at the other win-lose combination, and you probably can see the theme here. In this case, our entropy is going to be unfavorable, and having an exothermic reaction, that's going to be a favorable process. So looking at what we have here too, unfavorable entropy, sure, we've got gas as reactant that we make into a solid. That's unfavorable entropy. So that's consistent with what we'd be able to predict with this chemical reaction. In this case, our entropy is a losing parameter. We want to diminish its contributions, so we're going to favor these processes by decreasing temperature. So decreasing temperature helps this reaction be more favorable. All right, so basically I've run you through the scenarios that's on an important table here. You could try to memorize this table, but I think it's easier to try to understand it and understand how those pieces play into this all-important equation for thermodynamics. And that's it for what we have for the second skill on thermodynamics and free energy.